discuss about the SDS phase gel electrophoresis. Okay, so in our previous videos we have discussed about the basic principle of electrophoresis, right? That means how the force due to how the electrical force involves in migration of the molecule, and how the force called frictional force opposes it. Now then we have discussed about the concept of electrophoretic mobility, that is the migration of molecule and under the electrical field. So we have discussed about the basic electrophoresis technique. So now we are going to see the type of electrophoresis technique. Okay, so from that video I am going to discuss about the SDS phase, then we will move to the other one. So suppose you have to know first thing that electrophoresis is performed for separation of mainly two kind of biological molecule. One is protein, another one is nucleic acid. Okay, for protein separation we use page, and for nucleic acid separation we mainly prefer agarose. So our today's topic is about protein, so we will focus on page. Okay, so polyacrylamide gel electrophoresis is the full form of page. Okay, so polyacrylamide is a component, not only a component, instead I should say it is a mixture of component that involve in the formation of the gel, through which the molecules will migrate on the basis of their molecular mass under the influence of electrical field. Okay, so polyacrylamide is consist of two components, I have told you. So these two components are acrylamide and bisaccharylamide. Let's move to the slide regarding this. Okay, so polyacrylamide is consist of two components, polyacrylamide and N-prime methylene bisaccharylamide, or commonly known as bisaccharylamide. So the structure for acrylamide is CH2 double bond CH CONH2, and for N-prime methylene bisaccharylamide is CH2 double bond CH C double bond O NH CH2 NH C double bond O CH double bond CH2. If you are having difficulties in remembering the bisaccharylamide formula, then I will told you a trick that let's focus on that two circle. Okay, so this is nothing but the acrylamide, right? CH2 CH C double bond O NH. That means two acrylamide are joined together by CH2. That is the N prime methylene bisaccharylamide, right? So in that way you can easily remember the acrylamide and bisaccharylamide formula. They are really important for MCQs as well as viva questions. So we have discussed that we use for protein separation polyacrylamide gel, right? Now the question is why. We can use agarose gel also, but why polyacrylamide? So the answer of that question is protein is relatively smaller rather than the nucleic acid, right? Because nucleic acid is extended structure, a protein is relatively compact, right? So polyacrylamide gel forms a matrix whose pore size is relatively low rather than the pore size created by agarose. Okay, so what is the advantage of this? So this, due to the presence of small pore size, we can separate this kind of compact particle in polyacrylamide gel well than in case of agarose, because agarose provides larger pore size, and this larger pore size cannot help us to separate our protein molecule very sensitively. That is the reason why page is preferred in case of protein separation, and in case of agarose the nucleic acid separation we cannot prefer page because they are relatively larger in size. So if we use page in nucleic acid separation, so then our molecule cannot move, right? So separation cannot be established. Although if we have fragment of nucleic acid, Okay, so in that case we can use page. That is why during the DNA sequencing procedure we performed page instead of agarose cell, right? We have discussed this in our recombinant DNA technology section. That is the reason why, because the polyacrylamide gel provides less pore size, which is more suitable for protein and nucleic acid fragments and RNAs. Okay, but when you are dealing with a total DNA molecule, just go for agarose gel electrophoresis. Polyacrylamide gel cannot help you. And we have learned that polyacrylamide is consists of two substances. One is acrylamide and bisacrylamide. So formula for acrylamide is CH2 C double bond CH CO NH2, right? So this acrylamide and another acrylamide, when joined with a CH2, then you can conclude that it is a structure of N prime methylene bisacrylamide. This is the structure of N prime methylene bisacrylamide. That is why the term bis is used. Now the size of the pore is determined by the concentration of the acrylamide, okay, as usual. Now the higher the concentration, the smaller will be the size of the pore. So if you use higher concentration of polyacrylamide, so that is the resolution of gel, right? And we have to keep in this in our mind, the resolution of the gel. Resolution of the gel is necessary. So what is this? Let's learn this in a very simple example. That suppose you are dealing with protein sample which is already in its denatured condition. Not only that, also it is in relatively smaller fragment, okay, and now you need to separate them. So that in such cases you have to use larger concentration of polyacrylamide, right? Because larger concentration of polyacrylamide will create a less pore size, okay, or smaller pore size. So with the help of this smaller pore size we can separate those delicate particles. But if your protein is intact, right, so in that case you have to lower your acrylamide concentration so that they will give you a larger pore, right, so that you can easily separate them. That is the idea. So we have to keep in our mind that we have to set the gel concentration on the basis of our requirement, right? Whether we are dealing with delicate particles or we are dealing with relatively larger particles, on the basis of which we are going to set the concentration. Now let's come here. Polyacrylamide gel electrophoresis can be divided into various types on the basis of the type of protein we are willing to separate, okay. So the most common type is the SDS page, and this kind of gel electrophoresis is preferred when we are willing to separate our protein molecule on the basis of their molecular weight only, okay. Here we are not willing to separate the protein on the basis of their charge or other kind of physical properties. In such cases we will prefer SDS page. This SDS page in turn divided into two parts. One is discontinuous SDS page, another one is continuous SDS page. Remember one thing, that in discontinuous SDS page there will be presence of two different type of polyacrylamide gel. One is resolving gel, another one is stacking gel. We will come into this topic. And continuous SDS page consists of only one kind of polyacrylamide gel, okay. Along with SDS page there are another kinds of page present. One is native page. So remember one thing, that in SDS page we are using denaturing element. We are using SDS, which is a anionic cation exchanger. Not only that, it is a detergent also. So it also denature protein. That means here we are simply willing to separate protein on the basis of their molecular weight. But whenever you are willing to separate protein on the basis of something, okay, but you are also willing to see its biological activity, okay, so in that case you have to prefer native page. Because remember, in native page we don't add any kind of denaturing agent, right? So protein will be in its intact or native shape. That is why this kind of page is called as native page. Okay. So along with native page, SDS page, there are another kind of page called isoelectric focusing, where we are using the property of protein called pi. This is the pH in which the protein do not migrate towards any of the electrode, right? So on the basis of the pi and on the basis of the differences in charges, we are using isoelectric focusing to separate protein. We will come into this topic too. And the last and important kind of protein separation is the 2D gel electrophoresis. So in case of 2D gel electrophoresis, remember we are using two different dimension to separate the gel electrophoresis. That is why name 2D. But remember here 2 dimension means not the conventional dimension, but here we are willing to indicate that 2D means here we are using two physical properties to separate the protein, such as one is molecular weight, another one is our isoelectric point, that is pi, or more specifically the charge. Okay. So that means 2D gel is nothing but a combination of isoelectric focusing and our SDS page gel electrophoresis, right? So that is the idea. So that is the common type of SDS page electrophoresis types. Okay, one is SDS page where proteins are separated on the basis of the molecular weight, and SDS page also can be divided into two parts. One is reducing SDS page, another one is non-reducing SDS page. Reducing SDS page means where we are adding the beta mercaptoethanol and dithiothiol. So beta mercaptoethanol we all know involved in breakage of the disulfide bond, so it is more sensitive testing, and another one is non-reducing SDS page. In that case we are not using beta mercaptoethanol, only SDS page, right? So that is, and we have also divided SDS page into another two kind. One is discontinuous SDS page and another one is continuous SDS page. Then we have seen the native page where proteins are separated on the basis of their molecular weight and they are in intact form. Okay, here we do not have use any kind of denaturating agent or anything, right? After that we have discussed about isoelectric focusing, and the last one 2D gel electrophoresis. I will explain you all the thing one by one. So I have told you. Now let me take a picture. So this is an example of continuous gel electrophoresis or continuous SDS page. Why? Because remember here we are using only one kind of gel or only a constant concentration of gel. Okay, and this example is the discontinuous gel electrophoresis, where there is two gel, one is running gel, another one is stacking gel. Okay, just there is a difference in concentration, that's it. So in case of stacking gel the pH is 6.6, 6.7 to 6.8, and in case of stacking gel the concentration of gel will be 4% acrylamide gel. Now you told me, wait a minute, in case of, let me write the concentration in case of running gel too. So in case of running gel the concentration of acrylamide will be 5 to 15%. Now you tell me in which gel the pore size will be smaller and in which gel the pore size will be relatively larger. Yes, obviously in case of stacking gel the pore size will be relatively larger, and here the pH used is 8.8 to 8.9. So that is the idea. Okay, now let's discuss the components of gel. Okay, so we have discussed the stacking gel and running gel have only differences in pH and the concentration of the gel, but the general components in both the cases are the same. But in continuous gel electrophoresis the pH and the concentration of the gel is constant throughout the gel. Okay, there is no difference. So let's discuss about the components of the gel. Okay, so how that polyacrylamide gel is formed. So I have discussed with you that polyacrylamide gel is mainly consist of two things. One is acrylamide, another one is bis acrylamide. Along with that, it consists of a compound called timid, and another is APS, that is ammonium persulfate. Remember, this timid and APS involved in cross linking of acrylamide and bis acrylamide. Okay, and the last one is 3HCl. So this is the main component of polyacrylamide gel electrophoresis, by which the polyacrylamide gel is formed, which is a matrix consists of pores that allows migration of molecule at different rate based on their molecular weight. Acrylamide, bisacrylamide, TEMED, 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 APS, ammonium persulfate, and last one is 3HCl. Okay. And another thing that you need to remember, that here the buffer that we use is the 3-glycine buffer. So 3 is here involved in maintaining the pH, okay, which is near about 8.2 to 8.3 here. Okay, so that is the various components of the polyacrylamide gel electrophoresis, and we have also discussed about buffer here, right? Now let's discuss about the basic principle of behind the SDS page, which is our main topic today. So this is the structure of SDS page, sodium dodecyl sulfate, which is a anionic detergent first of all, and it is a negative charge provider. Okay, it confers a net negative charge to any kind of protein, and it makes the intrinsic charge of that protein insignificant. So in presence of SDS, no matter whether your protein is positively charged or negatively charged, in presence of SDS all the protein become negatively charged except our histone. Okay, that is why during the SDS page the quantification of histone is not accurate. Now how that SDS protein binds? So remember one thing, suppose this is a pen drop tube where you have taken your sample and then you have added the SDS. Okay, so suppose this is the protein sample, SDS press will bind to this protein molecule roughly proportional to their molecular weight. Okay, one molecule of SDS will bind with 2 amino acid residue. Remember one thing. Okay, so the binding pattern of SDS is important for MCQ, that one molecule of SDS will bind with 2 molecule of amino acid residue. So SDS bind to most protein in amount roughly proportional to the molecular weight of the protein, about 1 molecule of SDS for every 2 amino acid residue. Then the thing is, the bound protein, I have discussed with you that the bound SDS contribute a large net negative charge, rendering the intrinsic charge of the protein insignificant and conferring on each protein a similar charge to mass ratio. In addition, SDS protein also partially unfold the protein so such that all the SDS bound protein assume a similar shape. Okay, that means SDS also act as a denaturing agent. It unfolds the protein partially so that all the proteins have a similar shape. That means what? That means during electrophoresis in presence of SDS, it allows the separation of protein on the basis of only the molecular weight, right? Because it makes all the protein near about negatively charged. Okay, it also makes all the protein of similar shape. So there is one category left by which we can separate our protein, that is molecular weight. So that is why in the case of SDS page electrophoresis, proteins are separated on the basis of their molecular weight, and once the separation is performed, it can be detected by using Comasi dye, which binds to protein but not to the gel. itself. Okay, so that means composite blue is more or less specific, right? But it is not so sensitive. Okay, it can only detect protein of 100 nanogram. It is the limit. Okay, so for more sensitive and delicate detection, we prefer silver stain. Okay, this silver stain will detect 0.1 to 1 nanogram of protein for you. So here I have discussed this most common and least sensitive, but it is specific because it do not bind with gel, so it does not gives you any kind of false result, right? Visualizes the band under UV light. Now the important thing here is, remember in my previous video I have discussed with you that gel electrophoresis is of two types, right? One is horizontal gel electrophoresis, another one is vertical gel electrophoresis. Okay, so vertical gel electrophoresis example is page polyacrylamide gel electrophoresis, and horizontal gel electrophoresis example is agarose gel electrophoresis. Okay, we are going to discuss with about agarose gel electrophoresis in our upcoming videos. So what is the actual idea of gel electrophoresis? Remember, suppose this is a Eppendorf tube where you have your sample. So you have added the SDS. This SDS bind to the protein in amounts roughly on the basis of their molecular weight. One molecule of SDS bind with 2 molecule of amino acid. Okay, and SDS will give a net negative charge to the protein molecule, rendering the intrinsic positive charge of the protein insignificant. Okay, that means all the protein become net negatively charged. Not only that, it also facilitates the unfolding of the protein partially, okay, such that all the SDS bound protein becomes similar in shape. Okay, that is now then once you have prepared your SDS treated sample, you will simply load them in the well that is created with the help of a comb. This is such kind of particles, such kind of apparatus which we can use to prepare our well. Okay, and remember, in the well we will put our loads as our samples, okay, in a very delicate manner. And as we have treated our protein with negative charge, so when they will migrate under the influence of an electrical field, they will migrate towards the positive electrode, right? So the positive electrode will be in that direction and negative electrode will be in the direction of the well. Okay, and direction setting is very important during the electrophoresis. If direction is somehow become altered, your entire results will be damaged. Not only that, your protein sample will also lost, because remember, if you have setted positive electrode here, then your protein will migrate towards this position and it will mixed with buffer, okay, and ultimately lost, because remember, here buffer present and here also buffer present. So that is why we have to also stop our protein whenever they come very close to the positive electrode, right, by simply switch offing the electricity. So that is the overall concept of SDS page gel electrophoresis. This is the first video from the topic SDS page electrophoresis. I will again come back with another video of SDS page where I will discuss with you about some small questions that you need to remember regarding SDS page. Then we will move to the isoelectric focusing. Okay, so till then, bye bye.